The goal of our project was to create a wearable device to identify static hand gestures in real time. Our device allows the use of static gestures as a natural way to control a device. Applications include advancing a presentation, playing and pausing music or TV, playing games, and more.
We utilize a transducer with a bandwidth of 25 kHz plus or minus 2, along with a voice pickup unit to capture surface acoustic waves. The transducer and the VPU are both placed in direct contact with human skin. This allows the transducer to produce SAWs, which will then be picked up by the VPU. The transducer is driven with a frequency sweep from 23 to 27 kHz with a period of 0.1 seconds carrying a square wave at 10% duty cycle. We chose a VPU over a standard microphone as it is much less affected by outside environmental noise compared to a traditional microphone. We found that a VPU without a transducer itself can identify sound-producing gestures or action-based gestures like snapping your fingers. However, we wanted to classify gestures which held state. Thus, we decided to drive a transducer with a particular waveform and use the associated VPU output to classify these stateful gestures. The ESP32S3 is used to read data from the VPU using I2S and streamed back to the laptop using Wi-Fi, and is powered by a portable USB charger. We utilize another ESP32 to create a private Wi-Fi network, allowing both the laptop and the ESP32S3 to send and receive data unit to capture surface acoustic waves. The transducer and the VPU are both placed in direct contact with human skin. This allows the transducer to produce SAWs, which will then be picked up by the VPU. The transducer is driven with a frequency sweep from 23 to 27 kHz with a period of 0.1 seconds carrying a square wave at 10% duty cycle. We chose a VPU over a standard microphone as it is much less affected by outside environmental noise compared to a traditional microphone. We designed and printed custom mounts for the VPU and transducer. They include loops to vary the size of the strap, creating a one-size-fits-all wearable. Edges for the strap were rounded to allow the strap to be adjusted quickly and to minimize discomfort to the user from any sharp edges on the bottom of the 3D printed mounts.
Prove that we are not just learning from noise, as we have visually verified there are different FFT magnitudes corresponding to each hand gesture state. When the transducer is driven from a function generator, we can see that for the open hand gesture, the FFT output maintains a state with the highest magnitude of around 6 million. For closed hand gestures, the highest is around 4 million. Clearly, we can visually see there is a distinct but constant FFT featurization state that corresponds to each specific gesture state. When we turn off the function generator, the transducer is no longer driven, and the FFT featurization of the VPU output is wide varying and not holding any sort of state. This seems to just be noise that the VPU is picking up.
In this video demoing our project, our gesture set consists of 3 different gestures: open hand, close hand, and 2-finger. Our training data consisted of 40 samples for each gesture, each sample consisting of 5 frames. Since our sampling rate is 96,000 Hz, and our frame length is 10,230 data points, this will mean our samples are about 0.5 seconds long. Ultimately, in this example, we were able to obtain high offline and good real-time classification accuracy. After collecting the training data, we evaluated the performance of various models and found the SVC model had 100% training accuracy. We then loaded the model into T4Train, where the model did a prediction every 5 frames, or about 0.5 seconds. Also, as you can see, as I change gestures, the model accurately classifies the current gesture, oftentimes within less than 1 second of me doing and holding the gesture. Additionally, as I slowly move between an open and closed gesture, the prediction momentarily changes to the 2-finger prediction before settling to the true correct closed prediction. This can be easily fixed by overlaying a state machine that makes sure the current prediction holds for at least 1 or 2 seconds before being allowed to be a valid prediction. In the next video, we demonstrate that our wearable can also be used while standing up. Using the same training data and model from the previous video, we are still able to achieve very high testing accuracy while standing up. All the gestures that we performed while sitting down are being classified perfectly while standing up. This highlights the potential robustness of our wearable to different hand or elbow positions. Being able to stand and perform hand gestures with our wearable allows unique and different applications to become a reality. For example, a person can use his or her hand gestures to advance their slides in a presentation, assuming the presenter is most likely standing on stage. As you can see, when I hold a gesture, the prediction is still holding constant and steady. It is not rapidly fluctuating or changing to another gesture before I actually change to that gesture. This shows some of the steady state static gesture capabilities that our system can recognize and predict.